Right now, in every direction you can look, the equations of quantum mechanics describe what is happening. And one consequence of those equations, if you take them seriously, is that every possible version of you continues to exist somewhere. Not just the version you experience, every version, the one that took the other turn at the corner this morning, the one that did not, the one that was born on a Tuesday rather than a Wednesday, the one that lived through events that, in your particular line of experience, did not occur. If you take the equation seriously, that is the strangeness we are going to walk through tonight. You do not need to hold every consequence. Some you will. That is enough. The interpretation we are about to discuss is one of several that have been proposed. It is, by any honest accounting, the strangest. It is also, by some careful arguments, the most natural reading of the mathematics. We have a couple of hours. If you have come here to rest, let this carry you. The strangeness we are about to walk through is, in some sense, in the foundations of the physics that governs everything around us. We do not need to choose what to believe tonight. We only need to walk through what is there. Now let us pull back. Let us begin not with the strangeness, but with the physics that produces it. The story begins in the first decades of the 20th century, when a small community of physicists working in Germany, Austria, Switzerland, Denmark, and a few other places gradually built up what we now call quantum mechanics. The construction was, in many ways, the great theoretical achievement of the past century. It began with attempts to explain certain anomalies in atomic physics, the way that atoms emit and absorb light, the way that small particles like electrons move through space, the way that the energies of atomic systems are quantized rather than continuous. The theory that emerged by the late 1920s was strange. It described the behavior of small systems using mathematical objects called wave functions. A wave function, in technical terms, is a complex valued function that contains information about the system. From the wave function, you can extract probabilities for various measurements outcomes. The wave function evolves over time according to the Schrödinger equation, named for the Austrian physicist Erwin Schrödinger, who wrote it down in 1926. The Schrödinger equation, as a mathematical object, is deterministic. Given the wave function at one time, the equation tells you what the wave function is at any later time. There is no randomness in the evolution. The future of the wave function is fully determined by the present. But the wave function is not directly observable. What is observable in any quantum mechanical experiment is the outcome of a measurement. When you measure a quantum mechanical system, you get a definite result. The system is, after the measurement, in a state corresponding to that result. So the question arose, how do we get from the wave function, which describes probabilities, to the definite result that we observe? This question, in the history of quantum mechanics, is called the measurement problem. It has been with us, in one form or another, for nearly a century. The standard answer, developed in the late 1920s and early 1930s, came to be called the Copenhagen interpretation. The name reflects the fact that one of its primary architects, Niels Bohr, worked in Copenhagen. The Copenhagen interpretation says roughly that when a measurement is made, the wave function collapses. The collapse is a random process, governed by the probabilities encoded in the wave function. After the collapse, the system is in a definite state, corresponding to the measured result. The collapse is, in this interpretation, an actual physical event. It is part of the dynamics of the theory. The Copenhagen interpretation is, by far, the dominant interpretation in standard physics textbooks. It is what most physicists learn. It is what most physicists use in their daily work. It has been, for nearly a century, the working framework of quantum mechanics. But it has problems. The collapse is an additional physical process beyond the Schrödinger equation. It is not derivable from the equation. It is, in some sense, an extra ingredient. Where does it come from? What triggers it? What distinguishes a measurement from any other kind of physical interaction? These questions, in the Copenhagen interpretation, do not have clear answers. The measurement is, in some sense, mysterious. The collapse also has uncomfortable implications. It violates time reversal symmetry. It is non-local in some formulations. It depends, in many treatments, on what is meant by an observer, which raises questions about the role of consciousness in physics that most physicists are uncomfortable with. These issues have led, over the decades, to alternative interpretations of quantum mechanics. There are several. The many worlds interpretation, which we are walking toward, is one of them. Let me hold the Copenhagen interpretation a little longer, because the dissatisfaction with it is what drove the search for alternatives. The Copenhagen interpretation says, in essence, that the wave function is a description of the system's state, and that measurements produce definite outcomes by causing the wave function to collapse. The collapse is probabilistic, with the probability of each outcome given by the Born rule, which relates the wave function's amplitude to the probability of measurement. This sounds clean enough. The trouble comes when we ask precise questions. What is a measurement? The Copenhagen interpretation does not give a clean answer. In some formulations, a measurement is anything involving a classical apparatus. But what makes an apparatus classical? The apparatus is itself made of atoms, which obey quantum mechanics. So at some level, the apparatus is a quantum system. Why does it not, then, obey the Schrödinger equation rather than the collapse postulate? Some physicists, notably John von Neumann, argued that the collapse must, in some sense, occur at the moment of conscious awareness by an observer. The collapse in this picture is associated with consciousness. This raised serious concerns. Does the wave function collapse when a cat looks at a measurement device? When a bacterium does? When a thermometer does? The line between conscious observer and inanimate apparatus is unclear. Other physicists, like Bohr himself, argued that the measurement is fundamentally an interaction between a quantum system and a classical apparatus, with no further analysis required. But this leaves the question of what makes the apparatus classical untreated. Still others tried to avoid the issue by treating the collapse as a practical approximation rather than a real physical process. This is in some sense the modern view in textbooks. The collapse is just a way of summarizing what happens when we interact with a system. It is not, in this view, a real physical event. Each of these positions has its problems. None has been definitively settled. The measurement problem has been with us for nearly a century, and it has not been solved. The many worlds interpretation in some sense sidesteps the measurement problem by denying that any collapse occurs. It says, the wave function evolves according to the Schrödinger equation. Always. Everywhere. There is no special process called measurement. There is just the wave function, following its deterministic evolution. This is, in some sense, the most natural reading of the mathematics. If we believe the Schrödinger equation, why not believe it all the time, for all systems, without exception? The answer in the Copenhagen interpretation is that the resulting picture would be too strange. The wave function would contain multiple branches, corresponding to all possible measurement outcomes. We would have to accept that all the outcomes happen, in some sense, simultaneously. Most physicists in the early days of quantum mechanics found this unacceptable. The many worlds picture seemed absurd. The Copenhagen alternative, with its mysterious collapse, was preferred. Over the decades, opinions have shifted. Some physicists have come to find the Copenhagen interpretation more troubling than the many worlds picture. The collapse, they argue, is an arbitrary addition to the theory with no clear physical mechanism. The branching of the wave function, by contrast, follows directly from the Schrödinger equation. This is the debate. It has been going on for many decades. It has not been resolved. Now let us pull back. The many worlds interpretation was first proposed by an American physicist named Hugh Everett III. Everett was a graduate student at Princeton in the mid-1950s. He worked under the supervision of John Wheeler, one of the most distinguished theoretical physicists of his generation. Everett's question was this: what happens if we take the Schrödinger equation seriously all the way through? What if we do not add an extra collapse postulate? What does the universe look like in that case? The answer, when worked out carefully, is strange. If the Schrödinger equation applies to everything, including the observer, then the wave function of the universe never collapses. The wave function continues to evolve deterministically. After a measurement, the wave function contains, in some sense, every possible outcome of the measurement. The observer who made the measurement is, in the wave function, in a superposition of having observed every possible outcome. This is the central claim of the many worlds interpretation. The wave function does not collapse. All possible outcomes occur in different branches of the universal wave function. Each branch is, in some sense, a separate world. Each contains its own version of the observer, having observed its own particular outcome. Everett's dissertation, completed in 1957, was titled On the Foundations of Quantum Mechanics. The interpretation was, at the time, called the relative state formulation. The many worlds terminology came later, primarily from Bryce DeWitt, who promoted the interpretation in the 1970s. When Everett's dissertation was first published, it was largely ignored. The Copenhagen interpretation was dominant. Most physicists found Everett's claims either uninteresting or absurd. Everett himself left academic physics not long after his dissertation was defended. He worked for the rest of his career in industry, on defense applications and operations research. The interpretation, however, did not disappear. DeWitt's promotion in the 1970s brought it to wider attention. Over the decades since, the many worlds interpretation has gained adherence. By the early 21st century, surveys of physicists working in quantum foundations show roughly 20 to 25% endorsing it as their preferred interpretation. It is no longer fringe. It is a mainstream position, though still a minority one. Let me hold one more aspect of Everett's history. After he completed his dissertation, Everett left academic physics. He worked at the Pentagon and various defense-related institutions for the rest of his career. He developed innovative methods in operations research, including dynamic programming techniques that are still used today. He died in 1982, at age 51. By that time, his interpretation had begun to be taken seriously by parts of the physics community, primarily through DeWitt's promotion. But Everett himself was largely outside the academic discussion of his own ideas. His daughter Liz Everett has said that Everett believed in his interpretation. He thought it was correct. He also, by some accounts, considered the implications for personal survival to be reassuring. The many worlds interpretation, in Everett's reading, implied that his own consciousness would continue, in some branches, regardless of any death event. Whether this was a genuine philosophical conviction or a personal coping mechanism is hard to say. Everett's life was, by various accounts, difficult. He suffered from depression. His relationship with his children was complicated. Whether his views on quantum immortality affected his behaviour in any meaningful way is unclear. In any case, the interpretation persisted after his death. It has gained adherence in the decades since. The picture has been refined. The implications have been worked out. The interpretation, in some sense, has had its own life beyond the lifetime of its originator. This is one of the textures of physics history. Ideas once produced take on their own existence. They are taken up by others. They are refined, debated, criticised, defended. They become part of the cumulative work of the field, regardless of what their original authors thought about them. Everett's interpretation is now part of that cumulative work. It is studied. It is taught, at least to graduate students working in quantum foundations. It is one of the active positions in the debate about the interpretation of quantum mechanics. We are walking through it tonight. Now, let me bring this closer. I want to walk carefully through what the many worlds interpretation actually claims, because the popular descriptions sometimes get it wrong. The interpretation does not say that there are many universes in any straightforward sense. It says that there is one universe described by a single, universal wave function. The wave function has many branches. Each branch is a component of the wave function. The branches are not separate universes. They are parts of a single quantum mechanical structure. The interpretation also does not say that everything that can happen does happen. It says, more carefully, that everything that is consistent with the laws of quantum mechanics does happen. Many things that we might imagine, violations of conservation laws, for instance, cannot occur in any branch. The branches respect the underlying physics. The interpretation also does not require any special role for consciousness. The branching does not require an observer. The branching happens, in some sense, whenever a quantum mechanical event leaves multiple components in the wave function. This is constantly happening. Trillions of branching events occur per second in any macroscopic system. What the interpretation does claim is that the wave function is real. The wave function is not a mathematical convenience or a representation of our knowledge. It is the actual physical state of the universe. All of its components are equally real. When you observe one outcome of a measurement, the many worlds interpretation says there are also branches of the wave function in which other versions of you observed other outcomes. those other versions are not less real than the one you experience. They are simply in different branches of the same wave function. This is the picture. Let me hold the picture for a moment by thinking through one concrete example. Suppose you flip a coin. The coin has heads on one side and tails on the other. You flip it. It lands. You look. In the Copenhagen interpretation, the coin lands with some probability of heads, some of tails. You observe one outcome. The wave function has collapsed to that outcome. In the many worlds interpretation, the coin lands in both states. The wave function has branched. In one branch, the coin is heads, and you observed heads. In another branch, the coin is tails, and you observed tails. For the coin flip to actually involve quantum mechanics, we need it to depend on quantum mechanical processes. An ordinary coin flip depends on classical mechanics. The initial conditions of the flip determine the outcome. But if we use a quantum mechanical event to drive the coin, the outcome is genuinely quantum. Imagine then a quantum-driven coin flip. Some quantum event has, say, a 50-50 chance of producing one outcome or the other. The coin's landing reflects that outcome. In the many worlds picture, both outcomes occur in separate branches. You, the observer of the coin, also branch. In one branch you saw heads, in another you saw tails. Each version of you has its own continued history, with its own memory of the outcome you observed. Both branches are equally real. In the many worlds interpretation, both versions of you are equally real. Neither is more important than the other. Now repeat this thought experiment for every quantum mechanical event in the universe. Every such event produces branching. The branches multiply astronomically. The total structure of the wave function, accumulated over all these branchings, is the picture the interpretation describes. This is what we are talking about. Let me hold this for a moment. The picture is, in some sense, demanding. It asks us to take the mathematics literally. It asks us to accept that the wave function, in all its components, is what is real. It asks us to accept that we, as observers, are also part of the wave function, and that there are branches of the wave function in which we are different from what we experience. This is, I want to emphasize, not the standard interpretation. The Copenhagen interpretation is the standard. Most physicists, when they teach quantum mechanics, use the Copenhagen framework. But the many worlds interpretation has been gaining ground. It is, in some sense, the most natural reading of the mathematics if you do not invoke an additional collapse postulate. Stay with me here. Let me also walk through what decoherence does in the many worlds picture, because the picture without decoherence is impractical, and the picture with it is much more compelling. Decoherence is a process by which the components of a wave function become entangled with the degrees of freedom of the environment. When a quantum system interacts with its environment, the wave function's components, which were coherent and capable of interfering with each other, become correlated with different environmental states. As long as the environmental states are different, the components can no longer interfere. In practical terms, this means that, for any macroscopic system, the components of the wave function, corresponding to different measurement outcomes, decohere extremely quickly. The decoherence time scales for ordinary objects are unimaginably short, fractions of a fractional second. What this means in the many worlds picture is that the branches of the wave function become effectively separate. They no longer interact with each other. They cannot, by any practical experiment, be brought back into coherence. They are, for all practical purposes, separate worlds. This is what makes the many worlds picture coherent. Without decoherence, the picture would face the difficulty that the branches could, in principle, interact and interfere with each other. We would, in everyday life, see strange interference effects between branches. We do not. The reason, in the many worlds picture, is decoherence. Decoherence theory has been developed extensively in recent decades. It is now a standard part of quantum mechanics, accepted by physicists of all interpretational persuasions. It does not by itself settle the question of which interpretation is correct, but it does explain why the macroscopic world appears classical despite being described by quantum mechanics. This is the part that is hardest to hold. The interpretation does not claim to be obviously correct. It claims to be a possible reading of the equations. The question of which interpretation is correct is, in some sense, an empirical question that we do not yet have the tools to answer. The different interpretations make the same predictions for all observable quantities. They differ only in what they say is really happening behind the predictions. This is why the question is hard. It is not, strictly speaking, a question that can be settled by experiment. It is a question about how to interpret the structure of the theory. Now let me bring this closer. I want to walk through the consequences of the many worlds interpretation, if we take it seriously, because the consequences are, in many ways, the strangest parts. The first consequence is that every quantum measurement, every quantum mechanical event, produces branching. In a macroscopic system, an enormous number of quantum events happen every second. Each event branches the wave function. The total number of branches accumulated over the history of the universe is unimaginably large. By some estimates, the universe has branched, since the Big Bang, by a factor of perhaps 10 to the 10 to the 100. That is one followed by 10 to the 100th zeros. The number is so large that no language has the words to make it meaningful. It is, by any sensible measure, infinite for all practical purposes. The number of branches is, however, a feature of the interpretation rather than a problem with it. The interpretation does not require us to count branches. It only requires us to accept that they all exist. The second consequence is that, in this view, every possible outcome of every quantum mechanical event has happened, somewhere in the universal wave function. The branches contain all possible histories. Some are like ours. Some are different in small ways. Some are different in profound ways. The differences range from microscopic to macroscopic. A radioactive atom that decayed in your particular branch might not have decayed in some other branch. A particle's spin that was measured up in your branch might have been measured down in some other branch. These differences, at the microscopic level, propagate over time. Eventually, they produce macroscopic differences, different histories, different worlds. The third consequence is that your own history is, in this view, one of many. You experience one particular branch, but there are other branches in which you experience different events. Different versions of yourself with different histories exist in different branches of the universal wave function. These versions are, in the many worlds interpretation, equally real to the version you experience. They are not hypothetical. They are not less real. They are simply not in your branch. This is one of the strangest claims. The versions of yourself in other branches are real. They experience their own lives. They have their own continuous consciousness. They are, in some sense, you. Let me hold this carefully. The claim is not that there are infinite copies of you running around in some metaphysical sense. The claim is that the universal wave function has components, and in each component there is a version of the observer who experiences that component. The observer in each component takes that component as their reality. All observers, in all branches, experience their branches as the real one. This is a coherent picture, given the assumptions. It is, however, strange. Stay with me here. Let me also walk through the Born rule in the many worlds picture, because the role of probability in the interpretation is one of the philosophically tricky aspects. In standard quantum mechanics, the Born rule says that the probability of a measurement outcome is proportional to the square of the amplitude of the corresponding component of the wave function. The rule has been verified to extraordinary precision in many experiments. It is a fundamental feature of the predictions of the theory. In the Copenhagen interpretation, the Born rule is a postulate. It is added to the theory as a separate principle. The probabilities describe the chance that each possible outcome will be the one observed when the collapse occurs. In the many worlds interpretation, however, all outcomes occur. There is no collapse. There is no random selection. So what do the probabilities mean? This is one of the major technical challenges for the interpretation. Various proposals have been advanced. Some say that the probability is, in some sense, the weight of each branch, with branches of larger weight being more numerous or somehow more substantial. Others say that the probability is what a rational agent should expect, given the structure of the wave function and an appropriate decision theoretic framework. Others say that the probability emerges from the typical structure of the universal wave function, with most observers finding themselves in branches whose weights are roughly consistent with the Born rule. None of these proposals has been universally accepted. The status of probability in the many worlds interpretation remains an active area of research. This is one of the technical difficulties of the interpretation. It is also one of the reasons that not all physicists accept it. The handling of probability is, in some sense, less clean in the many worlds picture than in the Copenhagen alternative. Different physicists weight this difficulty differently. Some find it a serious problem. Others find it manageable. The debate continues. Now let me walk to the quantum immortality claim, because this is, in some sense, the strangest consequence of the interpretation. The argument begins with the observation that you, as a conscious observer, can only experience branches in which you are alive. The branches in which you are dead do not contain a conscious you. If we identify you with the conscious experience of the observer, then you only exist in branches where you are alive. The argument continues. Anytime you face a death by quantum event, the wave function has branches in which you survive and branches in which you do not. By the previous observation, you only experience the surviving branches. From your subjective perspective, you always survive. This is the quantum immortality claim. It has been formalized in various thought experiments. The most famous is the quantum suicide thought experiment, attributed in various forms to Hans Moravec and others in the 1980s. The thought experiment goes like this. Imagine an observer enters a chamber containing a device. The device contains a single radioactive atom. The atom has a 50% chance of decaying within some time period. If the atom decays, the device kills the observer instantly. If the atom does not decay, nothing happens. In the Copenhagen interpretation, after the time period, the observer has a 50% chance of being alive and a 50% chance of being dead. In the many worlds interpretation, the wave function has split. In one branch, the atom decayed, the device fired, and the observer is dead. In the other branch, the atom did not decay, and the observer is alive. From the perspective of the observer who experiences the surviving branch, they have, with certainty, survived. They cannot by definition experience the dead branch. They only experience the alive branch. If the experiment is repeated, the same logic applies. With probability 1/2 each time, the observer survives. By the many worlds interpretation, the observer only experiences the surviving branches. After many repetitions, the experienced subjective experience is one of continued survival, despite the fact that the probability of having survived all the repetitions in the Copenhagen framework is vanishingly small. This is quantum immortality. The argument extends to ordinary death. Every moment your body experiences enormous numbers of quantum mechanical events. Some of those events could, in principle, lead to your death. In the many worlds interpretation, the branches in which those death-causing events occur and the branches in which they do not are both present in the wave function. By the observer survives only where alive principle, you only experience the surviving branches. Therefore, the argument goes, your subjective experience of life continues indefinitely. You will never, from your own perspective, die. You will always find yourself somehow alive. This is the claim. This is, in some sense, the strangest implication of the many worlds interpretation. Let me hold this for a moment. The claim is, I want to emphasize, controversial. Most physicists who endorse the many worlds interpretation do not endorse the quantum immortality claim. There are several problems with the argument. The first problem is identity. The argument assumes that the version of you in each branch is you in some meaningful sense. But identity, in a branching wave function, is not so simple. Are the different versions in different branches all you? Or are they different observers who happen to share a common past? The question is genuinely difficult. Different philosophers and physicists have given different answers. The second problem is the branching probability. The argument assumes that there is always some branch where you survive. But for ordinary death from old age or disease, the branches where you remain alive grow vanishingly rare over time. By the time you would otherwise die at age 90, the branches in which you remain alive are extremely improbable. The argument requires that even these improbable branches contain you in some meaningful sense. The third problem is the quality of the surviving branches. Even if there is always some branch in which you are alive, the typical surviving branch may not have you in good shape. After many decades of unlikely survivals, the version of you in the surviving branch is likely to be in a degraded state. Alive perhaps, but not enjoying life. The fourth problem is empirical. The claim makes no testable predictions. It cannot be verified or refuted. It sits in the foundations of the interpretation as an implication that, if you accept the interpretation, you must accept. But you cannot prove it true or false. So the claim is, in some sense, both controversial and ungrounded. It is a consequence of taking the interpretation seriously. Many physicists who take the interpretation seriously nevertheless do not endorse the claim. Stay with me here. Let me also walk through what the many worlds picture says about randomness. Standard quantum mechanics treats the outcomes of measurements as genuinely random. Each measurement, in the standard view, produces a random outcome according to the probabilities given by the Born rule. In the many worlds interpretation, this is not quite right. There is no fundamental randomness in the universe. The wave function evolves deterministically. Every outcome occurs. The apparent randomness is, in this picture, an illusion of perspective. Each observer experiences one branch, and from their subjective perspective, the outcome they experienced appears to have been randomly selected. But the wave function, as a whole, has no randomness in its evolution. This is a significant change in the conceptual picture. Standard physics has, since the early 20th century, accepted that the universe is fundamentally probabilistic at the quantum level. The many worlds interpretation takes this back. The universe in this picture is deterministic. The probabilities arise from the structure of the branching wave function and from the observer's position within it. Whether determinism is true at the foundational level is, of course, a question of interpretation. Different interpretations give different answers. The Copenhagen interpretation maintains the fundamental randomness. The many worlds interpretation rejects it. The Bohmian interpretation is deterministic but in a different way. For most working physicists, the practical predictions are unchanged. The Born rule still gives the expected frequencies of outcomes. The actions we should take are the same regardless of which interpretation we adopt. But the philosophical picture is very different. In one picture, the universe is fundamentally probabilistic. In another, it is fundamentally deterministic, with the probabilities arising from the structure of the wave function. Which is correct, we do not know. The matter is, as I have said, beyond what current experiments can decide. Now let me walk through what the many worlds interpretation actually says about identity, because the question matters for the immortality claim. In the many worlds picture, you, as a person, are a particular pattern in the wave function. The pattern has a continuous history through one branch. The pattern has, in other branches, slightly different continuous histories. The pattern in each branch is, by the structure of the wave function, distinct from the pattern in any other branch. The branches are decohered, which means they no longer interact with each other. The pattern in one branch does not influence the pattern in another. So in what sense are the patterns in different branches you? They share a common past up to some branching point. After the branching, they have separate futures. They are in some sense like identical twins separated at birth. They share genes. They share early history. But they are not the same person. This is, I want to emphasize, one possible reading. Other readings are possible. The question of identity in a branching universe is, philosophically, contested. If we accept this reading, the quantum immortality argument changes. The you that experiences the surviving branch is not the same as the you in the dead branch. The you that survives is not, in some strict sense, the same observer who entered the chamber. It is a continuation of that observer along one particular branch of the wave function. The observer who died is, in some sense, also a continuation of the same earlier person, just along a different branch. In this reading, the immortality is not so straightforward. The you that survives is one continuation. The you that died is another continuation. Both are equally valid continuations of the earlier observer. This is, in some sense, a less unsettling reading. The strangeness of immortality is reduced. Death is not avoided. It happens in some branches. The continuation in other branches is real, but does not, in this reading, represent escape from death. Different philosophers and physicists prefer different readings. The matter is not settled. Hold this. Let me also walk through the question of what happens in the branches that contain other observers. In the many worlds interpretation, there is not just one observer being branched. Every observer, including every other person on Earth, is also being branched continuously. This produces an extraordinarily complex structure. In your particular branch, you observed a particular outcome. In another branch, you observed a different outcome. But also in those other branches, every other observer observed their own outcomes, which may have been different from what they observed in your branch. The combined structure is unimaginably complex. The wave function contains branches corresponding to every possible combination of observations by every observer in the universe. The combinations multiply with each branching event. For most purposes, the combinations are decoupled. The branchings of one observer are essentially independent of the branchings of another, except when they share a common system being observed. When two observers observe the same quantum system, their branches become correlated. Each observer, in their own branch, sees the outcome that the other observer, in the same branch, also sees. This is the consistency requirement. In any single branch, all observers agree about what happened. The agreement is built into the structure of the wave function. What this means is that the many worlds picture, applied across many observers, produces a coherent picture of each branch. In each branch, all observers agree. They have consistent histories. They have consistent memories. The branch contains, in some sense, its own complete history. This is, in some sense, the strength of the interpretation. It produces, naturally, a picture of each branch as a complete coherent world. The observers in each branch can interact, communicate, and agree about events. The branch contains, in a meaningful sense, its own universe. But the picture is, when we step back, vastly complex. The universal wave function contains all these branches, with all their internal consistency, with all their separate observers having their separate consistent histories. The total structure is, in some sense, beyond any human ability to fully imagine. We can only, in our particular branch, experience our particular small portion of the structure. The full picture is, in some sense, conceptually present but experientially absent. The many worlds interpretation is, in some sense, a deeply philosophical position. The technical claims are about the wave function and its evolution. The interpretive claims, about what the wave function means and how to think about identity within it, are matters of careful debate. This is one of the textures of working on the foundations of physics. The mathematics is, in some sense, clear. The interpretations of the mathematics are far less clear. We are walking through one of those interpretations tonight. The interpretation has its adherents. The interpretation has its critics. The interpretation has its implications, including the strange one about immortality. Let me hold one more aspect. The way the interpretation has been received by the broader public is interesting in its own right. In popular culture, the many worlds interpretation has become a familiar idea. It has appeared in countless science fiction novels and films. The notion of parallel universes has entered everyday usage. The interpretation, in some sense, is one of the most recognizable concepts from 20th century physics, outside the technical community. The popular treatments are often simplifications or distortions of the technical interpretation. They sometimes treat the branches as fully separate universes, each entirely independent of the others. They sometimes treat them as universes that observers can travel between. They sometimes treat them as universes that interact in dramatic ways. The actual technical interpretation, as I have walked through, is more subtle. The branches are not separate universes in any travel-related sense. They are components of a single, universal wave function. They cannot, by the decoherence theory, interact in any meaningful way once they have decohered. The interpretation is, in some sense, more mathematically constrained than the popular treatments suggest. But the popular interest does, in some sense, capture something true about the interpretation. The picture of many parallel realities is dramatic. It invites imagination. It connects with deep questions about identity, choice, and possibility. The popular interest has, in turn, fed back into the academic discussion. The interpretation is taken more seriously, in part because it has captured the public imagination. The discussion is richer in part because of the cultural penetration. This is a particular feature of modern science. Deep physical questions, including questions about quantum foundations, are now part of cultural discussion in a way they were not in earlier eras. The many worlds interpretation has, in some sense, become a cultural artifact as much as a technical position in physics. Whether this is good for the field is a separate question. Some argue that the cultural treatments distort the technical issues. Others argue that the popular interest has been net positive, drawing more attention and resources to questions that deserve attention. Either way, the interpretation has been with us for nearly 70 years now. It has been studied, debated, and developed. It has influenced our thinking about the foundations of physics in ways that are still being worked out. Let me also hold for a moment the question of how this picture fits with our everyday experience of reality. Most of the time we experience a single, continuous self in a single, continuous world. We make choices, observe outcomes, remember the past, anticipate the future. The world appears stable and singular. The many worlds interpretation says that this appearance is, in some sense, an artifact of our subjective perspective. The world is, at the deepest level, branching constantly. Our experience of a single continuous self is the experience of one continuation among many. This is a major shift in perspective. Whether it is correct, we do not know. But if it is correct, our everyday intuitions about the singularity of reality are misleading. How should we hold this? Different people answer differently. Some find the interpretation, even if true, irrelevant to daily life. The other branches are inaccessible, so they do not affect our practical choices. Others find the interpretation, if true, somehow changes the felt sense of reality. The knowledge that other branches exist with other versions of us makes the singular reality of our experience feel slightly less complete. Both responses are coherent. There is no obviously correct way to integrate the interpretation into everyday consciousness. For most people who think seriously about the interpretation, the integration happens slowly, over time. The strange picture becomes more familiar. The implications, once startling, become absorbed. The practical impact remains small, but the philosophical orientation shifts. This is, perhaps, what happens when any deep idea enters the cultural consciousness. It is at first jarring. Over time, it becomes part of the background. The many worlds interpretation has been undergoing this process for several decades. It is, in some sense, partially absorbed. It is, in some sense, still strange. The absorption continues. Whether the interpretation is correct is, as I have said, an empirical question that we cannot yet answer. The interpretation makes the same predictions as the standard Copenhagen framework for any observable. The two interpretations are, in some sense, equivalent for practical purposes. They differ only in their claims about what the wave function is and how to think about it. This is the situation. This is where we are. Now let me bring this closer. I want to walk through what would actually need to be true for the quantum immortality claim to be meaningful. The first thing that would need to be true is that the many worlds interpretation is correct, as opposed to other interpretations like Copenhagen, Bohmian mechanics, or various objective collapse theories. We do not at present have a way to distinguish these. Multiple interpretations are consistent with all the data. The second thing that would need to be true is a particular view of identity. Specifically, that you continue in the surviving branches in some meaningful sense. As I have walked through, this is contested. The third thing that would need to be true is that there is always some branch in which you survive. For arbitrary causes of death, this is not obviously the case. Some causes of death are not really quantum mechanical in their origin. If a meteor hits the Earth and destroys all life, there is no branch in which life survives, at least not in any branch corresponding to anything like our world. The fourth thing that would need to be true is that the surviving branches contain a version of you that is recognizably you in some psychological sense. The surviving branches after many improbable survivals are themselves improbable. They may contain a deteriorated version of you, or a version that has been preserved only by extreme luck. When you string all four conditions together, the claim of meaningful quantum immortality requires a lot of assumptions, most of which are contested or unverifiable. The claim in this light is a thought experiment more than a robust prediction. It is one of the strange implications of one possible interpretation of quantum mechanics. It is not a guarantee of immortality. This is, I think, the most honest summary. Stay with me here. Let me also walk through how the quantum suicide thought experiment was developed in the literature. The thought experiment was articulated, in various forms, in the 1980s and 1990s. Different authors developed different versions. Hans Moravec, in his 1988 book, Mind Children, described a version of the thought experiment in the context of speculations about uploading consciousness to computers. Bruno Marchal developed a related version in his work on computational philosophy. Max Tegmark, in his work on the many worlds interpretation, presented a clear version of the thought experiment in the context of quantum mechanics. The basic structure of the thought experiment is the same across all these versions. An observer is subjected to a process that has a chance of killing them. The chance is governed by a quantum mechanical event. In the many worlds interpretation, both outcomes occur with the observer continuing to experience only the surviving branches. The various versions differ in details. Some focus on a single trial, others on repeated trials. Some consider classical probability, others quantum. Some address the question of identity carefully, others gloss over it. The common conclusion is that, in the many-worlds picture, the observer's subjective experience of survival is robust. They always find themselves alive, no matter how dangerous the procedure they undergo. This conclusion is, I want to emphasize, drawn from the interpretation plus additional assumptions about subjective experience and identity. Different assumptions lead to different conclusions. The matter is not settled. Tegmark, in particular, has been a vocal defender of the many-worlds interpretation and has discussed the quantum immortality argument in his work. He has, however, been careful to note that the argument is controversial and that he does not necessarily endorse it as a guide to action. The thought experiment, despite its provocative nature, is not generally taken as a recommendation for any particular behaviour. It is taken as an illustration of the strange implications of the interpretation when followed to its conclusion. Now let me walk through some of the related ideas in the foundations of physics, because the many-worlds interpretation does not exist in isolation. It is part of a broader landscape of interpretations and philosophical positions. The Copenhagen interpretation, as I have said, is the standard. It postulates wave function collapse upon measurement. The collapse is a physical process beyond the Schrödinger equation. The interpretation has been criticized for its ambiguity about what constitutes a measurement, but it remains the dominant working framework. Bohmian mechanics, also known as the pilot wave theory, is a different interpretation. It says that particles have definite positions at all times, and that the wave function guides the particles like a pilot wave. The particles follow deterministic trajectories. There is no collapse. The apparent randomness of quantum mechanics comes from our ignorance of initial conditions, not from any fundamental randomness in the theory. This interpretation reproduces the predictions of standard quantum mechanics, but adds a level of structure that the standard theory does not have. Objective collapse theories like the GRW theory of Girardi, Rimini, and Weber modify the Schrödinger equation to include spontaneous random collapses at low rates. The collapses are postulated to occur frequently enough for macroscopic objects to always be in definite states, but rarely enough for microscopic systems to follow the standard quantum behavior. These theories make predictions that differ slightly from standard quantum mechanics, in principle testable. The relational interpretation, due to Carlo Rovelli, says that the state of a quantum system is always relative to an observer. Different observers may have different states for the same system. There is no observer-independent reality. Cubism, or quantum Bayesianism, is another interpretation that treats the wave function as a Bayesian probability assignment by an agent. The wave function is not a property of the system, but of the agent's beliefs about the system. Each of these interpretations has its adherents. Each has its critics. None has been definitively established as correct. The many-worlds interpretation is one position in this landscape. It is in some ways the most ontologically extravagant. It claims that the wave function is real and that all its components are equally real. The result is an enormous multiplicity of branches, but it is also in some ways the most economical. It does not require any addition to the Schrödinger equation. It does not invoke a special role for observers. It does not require any new physical processes beyond standard quantum mechanics. It says simply that what the equation describes is what is real. This is the trade-off: conceptual extravagance in the form of many branches, in exchange for theoretical economy in the form of a single deterministic equation. Different philosophers and physicists weigh these trade-offs differently. Let me hold the philosophical debate for a moment. The history of physics shows that, at various points, the field has accepted strange conclusions when the mathematics demanded them. The Earth is not the centre. The universe is enormously larger than we initially thought. Time and space are not separate. Mass and energy are interconvertible. Subatomic particles exhibit wave-particle duality. Each of these conclusions was initially strange. Each was eventually accepted as part of standard physics. The strangeness in each case gave way to familiarity over time. The many-worlds interpretation is, in some sense, a candidate for the next such acceptance. The interpretation may, over the course of the next century, become the standard reading of quantum mechanics. Or it may remain a minority view, or it may be displaced by some new interpretation that we have not yet conceived. The history of physics also shows that the strange conclusions have generally been forced by experimental data. The motion of the Earth was forced by Newton's mechanics and Galileo's observations. The size of the universe was forced by Hubble's measurements. The interconvertibility of mass and energy was forced by relativity and confirmed by atomic and nuclear physics. The many worlds interpretation, by contrast, has not been forced by data. It is a theoretical possibility. The data is consistent with it, but does not require it. Other interpretations are equally consistent with the data. This is why the situation is unusual. The history of physics suggests that strange conclusions get accepted when data forces them. Here the conclusion is strange, but the data does not force it. The acceptance, if it comes, will be different from the historical pattern. We do not know how this will play out. The interpretation may, over time, gain enough support that it becomes the standard. Or it may not. The matter depends on developments that we cannot predict. Let me hold the question of consciousness in the many worlds picture, because consciousness is, in some sense, the central character of the quantum immortality story. In standard physics, consciousness is not part of the theory. Physics describes the behavior of matter and energy. Consciousness, whatever it is, emerges from the behavior of complex biological systems. The exact nature of consciousness and how it emerges is a question for philosophy of mind and neuroscience, not for physics. The many worlds interpretation, however, brings consciousness back into the discussion, because the quantum immortality argument hinges on what conscious experience does in the branching wave function. The argument assumes, in some form, that conscious experience is associated with a particular pattern in the wave function. The pattern in different branches has slightly different futures. The conscious experience in each branch follows the pattern's continuation in that branch. So far, this is fairly neutral. It does not commit to any particular theory of consciousness. It just says that conscious experience tracks the pattern of brain activity in each branch. The argument then takes a step that requires more commitment. It says that the conscious experience of a particular person continues only in branches where the brain pattern continues. In branches where the brain stops functioning because the person is dead, there is no continuing conscious experience. This is, in some sense, a claim about the relationship between consciousness and physical states. Specifically, it claims that consciousness requires a functioning brain, and that the conscious experience of a person continues only where their brain continues to function. Most physicalist theories of consciousness would accept this claim, at least in broad outline. But the details matter. The argument requires that consciousness be tied tightly enough to brain function that there is no continuation across a death event. This is a stronger claim than mere physicalism. It requires that there be no surviving substrate of consciousness in any other form. If consciousness has any non-physical substrate, or if it can in some way persist beyond the death of the brain, the argument changes. The quantum immortality conclusion may not follow. These are open philosophical questions. The argument in some sense is a contingent conclusion that depends on assumptions about the nature of consciousness, as well as the interpretation of quantum mechanics. This is one of the complications. The argument is not derivable from physics alone. It requires philosophical commitments about consciousness. Now let me come back to the quantum immortality claim. I want to walk through what the claim would mean, philosophically, even if it were correct. The claim is that the conscious experience of an observer continues indefinitely. From the observer's subjective perspective, they always find themselves alive. The branches in which they died are not experienced. This is, in some sense, an immortality of subjective experience. It is not immortality of the body. The body in many branches dies. The body continues only in the unlikely branches. So what continues is the subjective experience, the continuity of consciousness. In some philosophical sense, this is strange because it suggests that our subjective experience may not be representative of the broader range of possibilities. We may, in some sense, be in the lucky branch of our own consciousness. The unlucky branches contain dead versions of us. The lucky branch contains the version that survived to this moment. This anthropic-style argument has been applied to many situations. It is, in some ways, related to the anthropic principle in cosmology, which holds that we should expect to find ourselves in a universe that is compatible with our existence. The many worlds interpretation extends this to the level of individual, subjective experience. But it is, again, controversial. Most physicists who endorse the many worlds interpretation do not endorse the strong quantum immortality claim. The claim relies on assumptions about identity and survival that go beyond the physics. Let me hold this. The picture, when we sit with it, is this. We have a physical theory. The theory has multiple interpretations. One interpretation, the many worlds, says that all possible outcomes occur. From this interpretation, by additional philosophical assumptions, one can derive the strange claim of quantum immortality. The claim is not established. The claim is not verified. The claim is, in some sense, a derivation from a chain of premises, each of which is contested. But the claim is also, in some sense, a coherent reading of one of our best theories. It cannot be dismissed simply by waving it away. It sits there in the foundations as one of the possibilities the physics admits. This is the position. This is what we are walking through. Stay with me here. Now, let me walk briefly through the experimental status. Because despite what I have said about the interpretations being empirically indistinguishable, there has been progress on testing some related claims. Quantum mechanics, as a working framework, has been tested to extraordinary precision in many ways. The fundamental predictions of the theory have been verified across countless experiments. The theory is, by any reasonable standard, the most accurately tested physical theory we have. But these tests do not, in general, distinguish between the different interpretations. They test the predictions of quantum mechanics, which are agreed upon by all interpretations. They do not test the claims that distinguish one interpretation from another. There have been, however, attempts to test the boundaries between the interpretations. Decoherence theory, developed over the past several decades, has provided a quantitative account of how the apparent collapse of the wave function occurs in practice. The theory shows that, when a quantum system interacts with its environment, the components of the wave function become entangled with the environmental degrees of freedom. After a short time, the components are no longer able to interfere with each other. They become, for practical purposes, separate. They behave like classical separate states. Decoherence does not require any postulate beyond standard quantum mechanics. It is a derivation from the Schrödinger equation. It is, in some sense, what the many worlds interpretation says happens when measurements occur. The wave function does not collapse. It decoheres. The branches become effectively separate. This is, in some sense, a major support for the many worlds picture. The mechanism by which the apparent classical world emerges from quantum mechanics has been worked out. It does not require any new physics. It only requires the standard Schrödinger evolution applied to systems coupled to environments. Other interpretations, however, can also accommodate decoherence. The Copenhagen interpretation can take decoherence as describing the apparent collapse. Bohmian mechanics can integrate decoherence into its trajectory picture. The relational interpretation can treat decoherence as a feature of observer-system relationships. So decoherence, while consistent with the many worlds interpretation, does not establish it. The interpretation remains one of several. Various experiments have been done on macroscopic quantum superpositions. These experiments show that quantum mechanical superposition can persist at larger and larger scales under appropriate conditions. The current record is, perhaps, a superposition of states involving billions of atoms. The trend is toward larger and larger superpositions. If superposition extends to truly macroscopic scales, including to systems containing conscious observers, the many worlds picture becomes more concrete. The branches at the macroscopic level become, in some sense, more vivid. The picture of multiple branches containing different versions of conscious observers gains by these experiments some experimental footing. But again, none of this establishes the interpretation. The experiments are consistent with multiple interpretations. The empirical question of which interpretation is correct, if any, remains open. Stay with me here. Let me also walk through the question of what evidence there is, if any, for the many worlds interpretation specifically. As I have walked through, the interpretation is not directly testable. The different interpretations make the same predictions for all observable quantities. But there are, in some sense, indirect considerations that one could weigh. The first consideration is theoretical economy. The many worlds interpretation requires no additions to the Schrödinger equation. Other interpretations require additions. Theoretical economy, by some metrics, favors the interpretation with fewer additions. The second consideration is theoretical coherence. The many-worlds interpretation is, by various analyses, fully internally consistent. It does not require any special role for measurement, observation, or consciousness. The interpretation works the same way for any system, regardless of whether observers are involved. The third consideration is connections with other physics. The many-worlds interpretation, by treating the wave function as fully real, is compatible with various features of modern physics, including quantum field theory, decoherence theory, and some aspects of quantum cosmology. Other interpretations, by contrast, sometimes face difficulties in extending to these areas. The fourth consideration is philosophical naturalness. The interpretation treats quantum mechanics as a single, coherent theory, not requiring special features for measurement. This is in some sense more naturally aligned with the general scientific project of seeking unified descriptions. These considerations are not individually decisive. They are, in some sense, soft arguments. They suggest that the interpretation deserves serious consideration, even if it cannot be definitively tested. Different physicists weigh these considerations differently. Some find them compelling, some find them not compelling enough. The matter remains a question of judgment and aesthetics rather than direct empirical test. This is one of the textures of modern foundational physics. Some questions cannot be settled by direct test. They are settled, if at all, by accumulated weight of indirect considerations over time. Let me also walk through one more aspect of the picture, which is the question of what would happen as you age in the many worlds interpretation. As you grow older, the branches in which you remain alive grow rarer. The reasons are statistical. Diseases, accidents, age-related deterioration. All of these are processes that eliminate branches over time. The branches in which you remain in good health, in particular, grow rarer faster than the branches in which you remain alive at all. By the time you would, in ordinary statistics, be expected to die from old age, the branches in which you remain alive are a tiny fraction of the original branches. By the time you would expect to die from accumulated, improbable circumstances, the surviving branches are negligible. But, according to the quantum immortality argument, your subjective experience continues in those tiny branches. From your point of view, you find yourself alive. The fact that the branches are improbable does not affect your subjective experience. The trouble is that the branches in which you remain alive are increasingly weird. They involve increasingly unlikely combinations of events. They may, for instance, involve you surviving multiple, potentially fatal events through extraordinary luck. They may involve you being kept alive in artificial life support systems. They may involve, in extreme cases, dramatic medical interventions, or even some kind of preservation technology. The subjective experience in these branches would, presumably, reflect the actual state of the surviving person. If the surviving you is barely alive, your subjective experience is that of barely being alive. If the surviving you is in extended life support, your subjective experience is of extended life support. The argument in this light becomes less appealing. Subjective immortality, achieved by selection into improbable branches, is not necessarily a good outcome. The surviving you may not be in any state to enjoy survival. This is one of the critiques of the quantum immortality argument. Even if accepted, the implication is not necessarily attractive. The improbable branches that contain a surviving observer are not, in general, ideal branches. The observer in those branches may experience, in their subjective continuation, a series of increasingly strange and uncomfortable circumstances. This critique has been articulated by various authors. It does not by itself refute the argument. The argument says that subjective survival continues. The critique says that the survival is not desirable. Both positions can coexist. The argument may be correct in its terms. The implication may separately be unappealing. Now let me hold the philosophical situation for a moment. The many worlds interpretation is, in some sense, one of the most philosophically demanding pictures that modern physics has produced. It asks us to accept that reality is, in some sense, far stranger than our everyday experience suggests. It asks us to accept that the wave function, in all its components, is real. It asks us to accept that our experienced world is one branch among an enormous number. This is a heavy intellectual lift. Many physicists find it implausible. even if they cannot find any technical flaw in the interpretation. The intuition that there is one reality, one world, runs deep. The interpretation asks us to abandon that intuition. Some physicists embrace it. Some find it the most natural reading of the equations and follow it through to its conclusions. Some develop the implications, including the quantum immortality argument, with full philosophical commitment. Others find it unacceptable. They develop alternative interpretations that preserve a single reality. They argue that the cost of multiple branches is too high. The debate has been ongoing for over half a century. It shows no sign of being resolved soon. What we have at present is the interpretation in the literature. It is well developed. It is mathematically coherent. It is philosophically demanding. It has its adherents and its critics. The interpretation, when applied to questions about personal survival, produces the quantum immortality argument. The argument is, as I have walked through, controversial. It requires additional assumptions beyond the basic interpretation. Those additional assumptions are themselves contested. So we have a chain of debates about the interpretation of quantum mechanics, about the nature of personal identity in a branching universe, about the relationship between subjective experience and physical reality. The chain is long. The chain has not been settled. What we have done tonight is walked through one path through the chain. We have, in some sense, traced one possible line of thought from the Schrödinger equation to the quantum immortality conclusion. The line is internally coherent. The line is, however, one of several possible lines. Let me also walk through what we might call the average observer perspective on the many worlds interpretation. The interpretation says that there are many branches with various amplitudes. By the Born rule, branches with larger amplitudes are more probable. If we ask what the typical observer experiences, we should look at the branches with high amplitudes. These are the branches in which, by the Born rule, you would most likely find yourself if you sampled randomly. In the typical branches, things look fairly normal. The probabilities of various outcomes match what we observe statistically. The world appears in these typical branches, classical and predictable, with random events occurring at the expected frequencies. The atypical branches, by contrast, contain unusual sequences of events. They contain unlikely outcomes accumulated over time. They are, by the Born rule, less probable. They contain fewer observers, in the typical sense of weighted counting. The quantum immortality argument in some sense requires the observer's subjective experience to track the atypical branches, the branches in which improbable survivals accumulate over time. These branches are, by the Born rule, less probable. But by the survival selection principle, they are the ones the observer experiences. This is one of the tensions in the argument. The Born rule, taken at face value, would suggest that most observers are in branches with statistically typical outcomes. The quantum immortality argument requires that the subjective observer be in branches with atypical outcomes, namely the surviving branches. The tension can be resolved in different ways. Some interpretations of the Born rule allow the survival selection principle to operate without contradiction. Other interpretations make the principle problematic. The matter is, again, an active area of philosophical debate. For most working physicists who endorse the many worlds interpretation, the safer position is to use the Born rule for ordinary predictions of frequencies and probabilities, without committing to any strong claims about subjective survival across branching events. This is the cautious position. It allows the interpretation to be used as a theoretical framework without committing to the strange implications about personal identity and immortality. Now let me come back to the strangeness. The strangeness of the quantum immortality claim is, in some sense, the strangeness of taking a particular interpretation seriously and following it to its conclusion. The interpretation is not obviously wrong. The conclusion is not obviously absurd, given the interpretation. But the conclusion is, by everyday standards, very strange. It suggests that subjective experience persists indefinitely. It suggests that the version of you that has survived to this moment is the result of countless improbable survivals in countless branches of the wave function, each of which selected for your continued existence. It suggests that, going forward, you will continue to find yourself alive, regardless of what dangers you face, because you can only experience the branches in which you survive. This is strange. It is, in some sense, an immortality of consciousness, not of body. The body may, in any particular branch, die. but the consciousness, by selection, finds itself in the branches where it has not died. The claim is, again, controversial. The claim relies on assumptions that go beyond the basic physics. Many of those assumptions are themselves contested. But the claim sits there. It is one of the implications of one of our best theories, taken seriously. It is one of the things that modern physics admits as possible. Hold this. The picture, when we sit with it, is one of immense strangeness. The strangeness is not unique to this interpretation. Quantum mechanics, taken seriously in any of its interpretations, is strange. The world at the quantum level does not behave like our everyday intuitions suggest. The many worlds interpretation extends the strangeness to the macroscopic level. It says that the macroscopic world is, in some sense, also branching. Our experience of a single reality is, in this picture, a feature of our subjective experience, not of the underlying physics. This is, in some sense, the cost of taking the equations seriously. The equations describe a wave function that, if we do not postulate collapse, branches incessantly. The branching, if we take it as real, produces the multitude of histories that the interpretation describes. We do not know if this is correct. We may never know. The interpretations are, as I have said, empirically indistinguishable on any test we can perform. What we have is the interpretation, sitting in the literature, with all its implications. Stay with me here. Now let me walk through the question of what this means for our understanding of ourselves. If the many worlds interpretation is correct, then we are, in some sense, much more than our experienced selves. We are patterns in a universal wave function that has branches containing many versions of us, with many different histories. This is a humbling and unsettling thought. It suggests that the singular self we experience is not the whole picture. The full picture includes many other versions in many other branches, all of which are, in some sense, also us. It also suggests that the choices we make, in any given moment, do not exhaust the possibilities. In other branches, we made different choices. Those other versions of us are living their consequences. They are, by the interpretation, no less real than we are. This can be read in different ways. Some find it liberating. The full multiplicity of possible lives is, in some sense, all being lived. Nothing is lost. Every possible version of us has its chance. Others find it unsettling. The uniqueness of the self is, in this picture, diluted. There are many versions. The one we experience is not, in any strong sense, more important than the others. Most people who think carefully about the interpretation, I suspect, find it both. The picture has elements of liberation and elements of unsettlement. It is, in some sense, a different way of understanding the human condition than what we are used to. We do not, of course, have to accept the interpretation. We can choose to use the Copenhagen framework, which says that the wave function collapses and that the version of us we experience is the only one. We can use Bohmian mechanics, which says that there are definite trajectories and that the wave function is a pilot wave guiding them. We can use any of the other interpretations. The choice, in some sense, is up to us. The physics, on any of the interpretations, makes the same predictions about everything we can test. The differences are in the metaphysics. What we do tonight is walk through one possible metaphysics. The metaphysics is strange. The metaphysics has implications. We have walked through some of them. We do not need to accept the metaphysics. We only need to walk through it carefully. Now let me hold one more aspect of the picture. The many worlds interpretation, when applied to consciousness, raises questions about what consciousness is and how it relates to physical states. The interpretation does not, by itself, settle these questions, but it provides a framework in which they can be discussed. If consciousness is a pattern in the wave function, then conscious experience persists in branches where the pattern persists. If consciousness is more than that, perhaps something that requires a coherent self-model, then the picture is more complicated. The boundaries between branches and what it means to be the same observer across them become unclear. These are philosophical questions. They do not have agreed upon answers. Different views are held. The interpretation, in some sense, makes these questions sharper. It forces us to think about identity and continuity in ways that the standard quantum framework does not require. This is one of the contributions of the interpretation. It clarifies, even if it does not resolve, deep questions about the nature of selfhood. Stay with me here. Let me also walk through what would happen if we, as a civilization, eventually accepted the many worlds interpretation as the correct reading of quantum mechanics. The acceptance would, in some sense, changed the way we think about our place in reality, we would understand in this picture that our experienced world is one branch of an enormously richer universal wave function. The other branches would be, in some sense, real, but inaccessible. Some philosophical implications would follow. Questions of choice and contingency would take on different significance. Every possibility that we, in our particular branch, did not realize would be realized in some other branch. The richness of possibility would be, in some sense, exhaustive. Every choice that could have been made was, in fact, made somewhere. This might be liberating. It might be unsettling. Different people would respond differently. There would also be practical implications. The interpretation would, in principle, affect how we think about prediction and decision-making. If we accept that all possible outcomes occur, with various amplitudes, our model of the future would shift from a single future to a structured set of branches. We would, in some sense, be choosing between branches rather than predicting a single outcome. For most everyday purposes, the practical predictions would not change. The Born rule still gives us the expected frequencies of outcomes. The actions we should take in a given decision context would still be those that maximize the expected utility weighted by the amplitudes. But the conceptual framework would be different. We would think of ourselves as making choices that bifurcate the wave function rather than choices that select one outcome from many. The full structure of possibilities would be, in this picture, real. Whether widespread acceptance of the interpretation would change anything important in human life is, of course, an open question. Most people, even physicists who accept the interpretation, do not let it affect their daily decisions. The interpretation in practice is a philosophical framework rather than a guide to action. Let me hold the cultural integration question for a moment. Many of the deep ideas of modern physics have, over time, been culturally integrated to varying degrees. The Big Bang theory is widely known. The expansion of the universe is part of general knowledge. Quantum mechanics, in some superficial form, is part of cultural discussion. The many worlds interpretation, despite being technical and philosophically demanding, has achieved a certain level of cultural recognition. The picture of parallel universes is familiar to many people, even if the technical details are not. This cultural recognition is, in some sense, an achievement of the field. The interpretation has been communicated to a broad audience. People can, in their casual conversations, refer to the idea. The notion of branches, of alternative selves, of multiple realities has entered the broader cultural vocabulary. Whether the recognition is helpful or distorting is a question of how the popular treatments handle the technical content. Some popular treatments are quite accurate, others are more flowery. The mix produces a complex cultural picture. For the field itself, the cultural recognition has had practical effects. Research on quantum foundations has more visibility than it did several decades ago. Funding has in some cases followed. Students are more interested. Books are more widely read. This is, in some sense, a positive feedback loop. The cultural recognition supports the field. The field continues to produce interesting work. The work feeds back into the culture. The many worlds interpretation is, in this sense, one of the success stories of communication between cutting-edge physics and broader culture. The interpretation is widely known, even if widely misunderstood. Whether this is right or whether the interpretation has implications that should affect behavior is itself a deep question. Most working philosophers and physicists treat the question with appropriate caution. The interpretation is, in some sense, beyond practical action, because all the branches are realized. Now let me come, slowly, to a quiet close for tonight. We have walked through quantum mechanics. We have walked through the measurement problem. We have walked through the Copenhagen interpretation, which is the standard. We have walked through the many worlds interpretation, which is the strange one. We have walked through what the many worlds interpretation claims. We have walked through its consequences. We have walked through the quantum immortality argument, which is perhaps its strangest implication. We have not, at the end, decided which interpretation is correct. That is not a question we can decide tonight. It is not, in some sense, a question that can be decided by any straightforward argument or experiment we currently have access to. What we have done is walk through the structure of one possible interpretation and its consequences. The structure is internally coherent. The consequences are strange. The interpretation has its adherents and its critics. The interpretation cannot be ruled out by any available evidence. This is the situation. Now let me bring this closer. The strangeness of quantum mechanics is, in some sense, the strangeness of the foundations of our best physical theory. The theory, by every test we can perform, accurately describes the behaviour of the natural world at small scales. But the theory does not tell us, unambiguously, what is really happening behind the predictions. Different interpretations of the theory tell different stories. The many-world story is perhaps the strangest, but other stories also have their strangeness. The Copenhagen story has the mysterious collapse. The Bohmian story has the pilot wave guiding the particles. Each interpretation has its peculiarities. What this means is that, at the foundations, our best understanding of physical reality is not what it appears to be at the macroscopic level. The macroscopic world looks like a single classical reality. The underlying physics may be very different. The many worlds interpretation extends this to the most radical conclusion. The macroscopic world we experience is, in this picture, only one branch of a vast wave function. Our continuous experience is the experience of one continuous branch. Other branches contain other versions of us. If the picture is correct, our individual subjective experience is, in some sense, the experience of a particular continuation of the universal wave function. The continuation includes our memories, our perceptions, our sense of self. The continuation does not exhaust all the possibilities. Other continuations in other branches contain other selves with other experiences. Let me also walk through the question of how the many worlds interpretation relates to questions about free will. In standard discussions of free will, one of the central questions is whether our choices are determined by prior causes or whether they involve some genuine novelty. In a deterministic universe, free will is often considered problematic. Our choices in such a universe are fully determined by prior conditions. There is no real freedom. We are just following the deterministic evolution of the universe. In a probabilistic universe, free will is sometimes considered easier to accommodate. The randomness in measurement outcomes in standard quantum mechanics could be associated with genuine freedom. Our choices in this picture could involve some quantum mechanical randomness, that is, in some sense, free. In the many worlds interpretation, however, the picture is different. The Schrödinger equation is deterministic. There is no randomness at the fundamental level. All possible outcomes occur. The branching's fully determined by the wave function's evolution. What this means for free will is, in some sense, complex. If we identify with one branch, then our choices in that branch are determined by the wave function's evolution. There is no randomness selecting which branch we end up in. Both branches occur. In some sense, the choice was already encoded in the wave function from the start. But the picture also says that we, in some sense, are in all the branches. Each branch contains a version of us making a particular choice. We are, in some sense, all of those versions, each making its particular choice. This is, in some sense, a different way of understanding choice. The choice is not a selection from possible outcomes. It is the bifurcation of the wave function into branches each containing one of the outcomes. Whether this picture preserves anything resembling free will is, of course, a philosophical question. Different thinkers reach different conclusions. Some find the picture compatible with free will, in a sense. Others find it incompatible. The matter, like much else about the interpretation, is not settled. Let me hold one more philosophical question. If we are, in fact, in a branching wave function, with multiple versions of ourselves in different branches, what is the moral status of those other versions? In ordinary ethical thinking, we worry about the well-being of other beings. We care about the suffering of other people. We try to act in ways that reduce overall suffering and increase overall flourishing. In the many worlds picture, however, our actions in our particular branch do not affect the other branches. The other versions of us are doing their own things. We cannot, by any choice we make, change what happens in another branch. Does this mean we have no moral obligations to the other branches? Or does it mean that we have obligations to all branches, but cannot fulfill them across branches? These are deep questions. Philosophers have begun to explore them. Different positions have been articulated. Some argue that moral obligations are confined to our branch. The other branches are causally disconnected from ours, so they cannot be affected by our choices. Our moral focus should be on our own branch. Others argue that even if we cannot affect other branches, the existence of suffering in other branches is morally significant. We should perhaps be concerned about the overall structure of the wave function including the branches we do not experience. Still others argue that the question is incoherent. Identity in a branching universe is not clear enough for moral obligations to be assigned across branches. The matter is, again, philosophical and unsettled. But it is one of the questions the interpretation raises. For most working physicists and most ordinary ethical practice, the many worlds interpretation does not change much. We act in our branch. We try to do good. We do not worry about the other branches because we cannot affect them. Let me hold one more thought about the implications. The many worlds interpretation, if correct, suggests that the cosmos contains, in some sense, all possibilities consistent with the physical laws. Every event that could have gone differently did go differently somewhere. Every choice that could have been made differently was made differently somewhere. This is, in some sense, a vast richness. The cosmos is not just what we experience, it is the entire structure of possibilities, all realized, all coexisting in the universal wave function. We, in our small branch, experience one slice of this richness. The slice we experience is, for us, the whole of our subjective reality. But the underlying structure, if the interpretation is correct, is vastly larger. This is in some ways the most cosmologically humbling implication of any modern physical theory. We are not in the only world, we are not in the most important world. We are in one slice of an enormously larger structure. The implications of this for our self-understanding, our sense of meaning, our cultural narratives, are all profound. They are also in some sense beyond our current ability to fully integrate. We continue to think about them, but we have not arrived at a settled cultural response. The interpretation, and its strange implications, will likely be with us for many decades to come. The thinking will continue. The picture will perhaps slowly become more familiar. Or perhaps it will be displaced by some new interpretation that we have not yet conceived. We do not know. We watch the development of the field. We participate in our small ways as observers of one of the deepest open questions in modern physics. But the question is there, the interpretation, if taken seriously, raises it. We do not have to answer it, but we have noticed it. This is the picture. We do not know if it is correct. We continue to think about it. Hold this. The thinking about it is, in some sense, the work. The interpretation has been with us for nearly 70 years. The thinking continues. Each generation of physicists and philosophers contributes new analyses. The picture, slowly, refines. We do not, in our lifetimes, expect to settle the question of which interpretation is correct. The question may not be settleable in principle. The interpretations may simply be alternative ways of organizing the same predictions. But the thinking continues. The discussions continue. The debates continue. This is the texture of working on the foundations of physics. The questions are deep. The answers are partial. The work goes on. Let me also hold the personal dimension. For an individual physicist or philosopher working on the interpretation, the engagement is intellectually demanding. The technical issues require deep familiarity with quantum mechanics. The philosophical issues require careful reasoning about identity, probability, consciousness, and metaphysics. Few people develop the full set of skills required. Those who do are part of a small community working on quantum foundations. The community communicates, debates, refines. The work is, in some sense, a specialized intellectual ecosystem. The rest of us, working physicists or interested observers, can read the literature and follow the arguments. We can hold the picture in mind. We can think about its implications. But we are, in some sense, observers of the work rather than participants in it. This is the typical structure of deep intellectual fields. A small core of specialists does the technical work. A broader audience follows. The audience does not, in itself, advance the technical work. But the audience does, in some sense, sustain the cultural attention that allows the field to continue. We, as the audience tonight, are doing this work. We are paying attention to a deep, technical, and philosophical question. We are, in our small way, holding the question in our awareness. We are participating, modestly, in the broader project of thinking about the foundations of reality. This participation is, perhaps, what observers can do. We notice, we consider. We do not by ourselves advance the field. But we do, by our attention, sustain the cultural conditions in which the work goes on. The work is being done. We have walked through a piece of it tonight. If you have come here to rest, let this carry you. The strangeness is in the foundations of the physics that governs everything around us. We do not need to choose what to believe tonight. We only need to walk through what is there. What is there is strange. What is there is also our best current understanding of the small-scale behavior of the natural world. The strangeness and the understanding go together. We sit with the strangeness. We try to make sense of it. We continue. Now, let me come back briefly to the immortality claim. The quantum immortality argument is, as I have walked through, controversial. It requires additional assumptions beyond the basic many worlds picture. The assumptions are about identity, about which branches you continue in, about what counts as survival. The assumptions are not settled. Different careful thinkers reach different conclusions about them. For most working physicists, the practical attitude is to suspend judgment. The interpretation is one of several possibilities. The immortality argument is one of several possible derivations from the interpretation. We do not need to decide tonight. What we have done is walk through the structure of the argument. We have, in some sense, seen what kind of conclusion the interpretation produces when followed through. The conclusion is one of the strangest implications of one of our best theories. It cannot be tested. It cannot be ruled out. It sits in the foundations as one of the possibilities the physics admits. We do not need to accept it. We only need to acknowledge that, given certain interpretive choices, it follows. Stay with me here. Let me also walk briefly through how the many worlds interpretation relates to other strange ideas in modern physics. The interpretation does not exist in isolation. It is part of a broader landscape of strange ideas about the nature of reality at the deepest level. Some of these strange ideas come from cosmology. The inflationary cosmology, which is the standard model of the very early universe, suggests that there are vast regions of space outside our observable universe. Some versions of inflation suggest that there are entirely separate bubble universes that may have different physical laws from our own. This is sometimes called the multiverse, but in a different sense than the many worlds interpretations branches. Other strange ideas come from string theory. Some versions of string theory suggest that there are many possible vacuum states, each corresponding to different physical laws. The full space of possible string theory vacuum states is called the landscape. Different regions of the multiverse may, in this picture, sit in different vacuum states. These different multiverses, the many worlds branches, the inflationary bubble universes, the string theory vacua, are conceptually distinct. They arise from different theoretical considerations. They have different structures and different implications, but they share a common theme. Modern physics, taken seriously in various contexts, suggests that reality is far larger and more varied than our everyday experience indicates. Whether through quantum branching, cosmological inflation, or string theory landscapes, the universe we experience may be one component of a much vaster whole. Whether this is correct in any of its forms, we do not yet know. The various multiverse pictures are theoretical possibilities. None has been definitively established. But the cumulative effect of these pictures is to suggest that, at the deepest levels, the universe may be larger and more varied than our intuitions allow. This is, in some sense, what philosophy of physics looks like. The mathematics is, broadly speaking, clear. The physical content of the theories is, broadly speaking, clear. The interpretation of what the theories say about reality is far less clear. We work on the interpretations, we argue, we debate, we propose, we refine. The interpretations evolve over time, even if no consensus emerges. This is the work. Tonight we have walked through one interpretation and one of its strangest implications. We have not decided, we have not concluded. We have walked through. That, in some sense, is what we can do. Let me also walk briefly through what concrete progress in the foundations of physics might look like in the coming decades. There are several lines of work that might, in principle, shed light on the questions we have been discussing. The first line is experimental work on macroscopic quantum superpositions. As I mentioned, the current record for macroscopic superpositions involves systems with billions of atoms. The next decade may see this extended to larger and larger systems, potentially including small biological samples or other systems that approach the scale of everyday objects. If superposition can be extended to truly macroscopic scales, the many worlds picture becomes more concrete, and the alternative interpretations face increasing pressure. Specifically, objective collapse theories would be tested. If they predict that superpositions cannot extend beyond a certain scale, and we can verify superposition beyond that scale, the objective collapse theories would be falsified. The second line is theoretical work on the foundations of quantum mechanics. Philosophers and physicists continue to refine the interpretations, work out their implications, and propose new interpretations. The cumulative work over decades may produce a clearer picture of what the different interpretations entail and where they differ. The third line is connections with other parts of physics. Quantum gravity, in particular, may shed light on the foundations of quantum mechanics. If we understand how gravity is quantized, we may learn more about how quantum mechanics applies to space-time itself. This may have implications for the interpretation of the wave function. The fourth line is connections with consciousness research. As our understanding of how brains produce conscious experience improves, we may better understand the relationship between physical states and subjective experience. This may, in turn, inform the philosophical discussions about identity in branching universes. Each of these lines of work is active. Each may, over decades, contribute to a clearer picture of the foundations. We do not, of course, know what the picture will look like. It may be that one interpretation emerges as clearly preferred. It may be that the interpretations remain underdetermined by the data, but that some are eliminated by new theoretical considerations. It may be that entirely new interpretations are developed that subsume or replace the current ones. The work continues. Now let me sit with one final thought. The many worlds interpretation, regardless of whether it is correct, has changed the way many people think about the foundations of physics. It has demonstrated that the natural reading of the Schrödinger equation, without any additional collapse postulate, produces a strange but coherent picture of reality. The picture is, in some sense, a possibility that has to be taken seriously. Other interpretations, by contrast, must explicitly add structure to avoid the many worlds conclusion. They must postulate collapse, or pilot waves, or relational structure, or something else. Each of these additions is a choice. Each is a way of avoiding the multiple branches. The many worlds interpretation, in this sense, is the interpretation of austerity. It says, take the equation as given. Do not add anything. The result is what you get. The result is many worlds. This is one of the deep things that modern physics has revealed. The natural mathematical structure of one of our best theories, taken at face value, produces a picture of reality that is far stranger than what our everyday experience suggests. We may, in the end, find reason to add structure and avoid the conclusion. Or we may, in the end, accept the conclusion as the natural reading. The choice has not been made. The choice may not be makeable in any decisive way. What we have, at this moment, is the possibility. The interpretation is in the literature. The implications are debated. The work continues. Let me also walk briefly through one more conceptual aspect of the picture. The many worlds interpretation, by saying that all possible outcomes occur, is in some sense democratic about realities. Every possible reality, consistent with the laws of physics, is, in this picture, instantiated somewhere. This is, in some sense, an attractive feature. It eliminates the apparent arbitrariness of why this particular outcome rather than another. In the many worlds picture, both outcomes happen. Neither is privileged. The apparent arbitrariness disappears. It is also, in some sense, a deeply egalitarian view of reality. Each branch is equally real. No branch is preferred. The branch we experience is not better or more important than any other branch. We just happen to be in one. This egalitarian view has its own consequences. It suggests that we should, in some sense, treat all branches as equally significant. The outcomes in our particular branch are no more important in the cosmic scheme than the outcomes in any other branch. For most ethical and practical purposes, this is not a concern. We act within our own branch. We make decisions based on what we experience. The fact that other branches exist, with different outcomes, does not generally change our behavior. But the philosophical implications are real. The many worlds picture, taken seriously, decenters our particular experience. We are not in the only world. We are not in the most important world. We are simply in one world among many. This is, in some sense, the deepest decentering that any physical theory has produced. Copernicus moved us from the center of the universe. Hubble moved us to one of many galaxies. Now, Everett's interpretation, if correct, moves us to one of many parallel realities. The decentering, when we sit with it, is profound. It is, in some sense, the latest in a series of cosmological humblings. Each humbling in its time was disorienting. Each over time became familiar. The many worlds interpretation may eventually become familiar in this same way. Or it may not. We do not know. What we have is the picture. We are walking through it. Hold this last image. Right now, in every direction you can look, the equations of quantum mechanics describe what is happening. The equations, if we take them seriously, suggest that every possible thing that could happen is happening somewhere in the universal wave function, that somewhere is, in this interpretation, real. The wave function is real. Its components are all real. Our particular experience branch is one component among many. Whether this is correct, we do not know. The picture cannot be tested. The picture cannot be ruled out. What it is a possibility. One of the deepest possibilities that modern physics admits. Let me also hold the question of what scientific progress looks like on questions like these. The interpretations of quantum mechanics are, in some sense, philosophical positions about what the mathematics means. The mathematics itself is fixed. The interpretations differ in how they read it. This is unusual by the standards of most scientific questions. In most areas of science, we have hypotheses that make different predictions, and we test the predictions. The hypothesis whose predictions match the data wins. In the interpretations of quantum mechanics, the predictions are the same. The hypotheses cannot be distinguished by experiment. The choice between them is, in some sense, aesthetic or philosophical. Some thinkers have argued that this means the interpretations are not really scientific. They are metaphysical positions, not testable theories. The argument has some force. If we cannot distinguish the interpretations by experiment, in what sense are they doing the work of science? The counter-argument is that the interpretations matter for how we think about the foundations of physics. The interpretations shape our intuitions, our pedagogy, our metaphysical commitments. Even if they cannot be tested, they have intellectual content. They are part of the broader scientific enterprise of understanding the nature of reality. This debate about the status of the interpretations is itself ongoing. Different thinkers reach different conclusions. The matter is not resolved. What is clear is that the interpretations are not going away. They have been with us for nearly a century. They will, in all likelihood, continue to be discussed for many more decades. The many worlds interpretation is one of them. It is one of the most strange. It is one of the most radical. It is one of the candidates for the correct reading of quantum mechanics. We continue to think about it. We have walked through it tonight. Let me hold one more time the elegance of how this picture emerges. Quantum mechanics gives us the Schrödinger equation. The equation is deterministic. It tells us how the wave function evolves over time. The evolution is, by every test, accurate. The puzzle has been how to reconcile this deterministic evolution with the apparent randomness of measurement outcomes. The Copenhagen interpretation invokes a special collapse process. The many worlds interpretation does not. It says that the wave function, in its full evolution, contains all the outcomes. The apparent randomness is a feature of the observer's position within the wave function. This is, in some sense, the most economical reading of the physics. We do not need to add anything to the Schrödinger equation. We just need to take it at face value, all the way through. The cost, of course, is the strange picture of many branches. The benefit is the conceptual cleanness of not requiring an additional collapse postulate. Different physicists weigh the cost and benefit differently. Some find the cost too high and prefer the Copenhagen interpretation. Some find the cost worth paying and prefer the many worlds interpretation. Some find both unacceptable and pursue alternative interpretations. The choice has not been made. The choice may not be makeable in any decisive way. What we have at the end of all of this is the picture in the literature. The interpretation is one of the candidates. The implications, including the strange one about immortality, sit in the foundations as part of what one might commit to. We do not have to commit. We can simply walk through. Walking through is what we have done tonight. Let me hold one last consideration. The many worlds interpretation is, as I have said, one of several interpretations. The competition between interpretations is, in some sense, healthy for the field. It keeps the foundations active. It generates new analyses, new arguments, new perspectives. Even if the interpretation is eventually rejected, The discussion of it has improved our understanding of quantum mechanics. We understand decoherence better, in part because we have had to ask how the apparent classical world emerges from a non-collapsing wave function. We understand the structure of the wave function better, in part because we have had to take its branches seriously. This is, in some sense, what philosophical foundations work does. It deepens the understanding, even when it does not produce definitive answers. The many worlds interpretation has done this work for us. It has, regardless of its ultimate truth, contributed to our understanding of quantum mechanics. The contribution is real, even if the interpretation turns out to be wrong. We are beneficiaries of all this thinking. The understanding we have today of decoherence, of measurement, of the structure of the wave function is richer than it was before the interpretation was developed. The discussion has improved our framework. This is one of the textures of how science develops. Even contested ideas, even ideas that may eventually be rejected, contribute to the deepening of our understanding. The contribution does not require the ideas to be correct. It requires only that they be taken seriously and worked through. The many worlds interpretation has been taken seriously. It has been worked through. The contribution is now part of the cumulative knowledge of the field. We have walked through it tonight. Hold this. The picture is, in some sense, our deepest current account of what reality might be at the quantum level. The picture is not settled. The picture has its critics. The picture has its strange implications. But the picture is there. The interpretation has been developed. The work has been done. The thinking continues. We are, in some sense, beneficiaries of all this thinking. We can, in our small evening, consider what some of the strangest thinkers in modern physics have produced. We can walk through their conclusions slowly, without committing. The walking through is itself, in some sense, a participation in the work. We do not solve the problem. We do not advance the field. But we do, in our small way, hold the question. We do, in our quiet way, take the issue seriously. That is, in some sense, what observers can do. We notice. We consider. We engage with the deep questions of our cosmic situation, the many worlds interpretation, the quantum immortality argument, the strange branching wave function picture. These are part of the deep questions. We have walked through them tonight. Let me hold one last image. Quantum mechanics, taken seriously, describes a world that is far stranger than our everyday experience suggests. The wave function, in its full structure, contains many possibilities. The classical reality we experience is one slice of that structure. Whether the slice we experience is unique, or whether all the other slices are equally real, is the question that the interpretations of quantum mechanics try to answer. Different interpretations give different answers. The many worlds interpretation gives the most radical answer. All the slices are real. We experience one. The others contain other versions of us, having other experiences. This is, in some sense, the deepest reframing of reality that modern physics has produced. The everyday singular reality we experience may be, at the deepest level, one component of a much larger structure. We do not know if this is correct. We have walked through what it would mean if it is. That walking through is, in some sense, what we have done tonight. Let me hold one more aspect of the picture before we close. The many worlds interpretation is, in some sense, the natural reading of one of our most successful theories. Quantum mechanics is the best tested theory in all of physics. Its predictions have been verified across countless experiments to extraordinary precision. That this best tested theory, taken at face value, implies the existence of many parallel branches of reality is, in itself, a striking fact. Whether we accept the interpretation or not, the fact that our best theory naturally produces this picture is worth holding. The success of quantum mechanics, combined with the strangeness of its natural interpretation, suggests that reality at the deepest level may not be what our everyday experience indicates. The world we experience may be a slice of a much larger structure. This is the situation we are in. We have an excellent theory. The theory, taken seriously, suggests a strange picture of reality. We do not know if the picture is correct, but we cannot easily dismiss it. We have not arrived at a conclusion tonight. We have perhaps arrived at a clearer understanding of what is at stake. Thank you for staying with me through this story.